So your book might present this with a picture here. The different values of the sequence are moving along the number line. And epsilon here you can think of as controlling how far we have zoomed in, how far we have magnified this scatter plot. Now, another way to visualize this is to, again, think of the sequence as a function, right? So input 1, output first element of the sequence. Input 2, output second number in the sequence. Input 3, output third number in the sequence, and so on. And that lets us graph these out, just like we would graph a function, only my domain consists of integers, not all real numbers. So my graph consists of just these discrete points. So again, I can represent that in Desmos, and I'm using this same trick where I specify a list of numbers in brackets. And now if I turn this part of the graph on, these blue dots are representing the very same sequence that I had in my previous clip, where the first term of the sequence is 1/2, the second term of the sequence is 1/4, the third term of the sequence is 1/8, and so on. And I find all of that out based on the formula right here. The nth term of the sequence is 1 divided by 2 to the power n. And so this gives us a different picture of the very same information. The farther I go out to the right, the closer my sequence values get to 0. And in fact, starting at n equals 11, Desmos itself cannot tell the difference between these sequence numbers and 0, because computers can only work with finitely many decimal points. So a different way we can think about sequences is to say, well, I've got this very nice formula here. The nth term of the sequence is 1 divided by 2 to the power n, and n is an integer. In fact, my n's for this diagram only go up to 16. But there's nothing stopping us from trying real numbers in that formula, and I'd get something that looks like this: y equals 1 on 2 to the power x. So just a very simple exponential decay. And if this was calculus 1, I could say, well, we can just trace our finger along the graph here. And as x goes to infinity, then the value of this function is going to go to 0, right? The limit of 1 on 2 to the power x as x goes to infinity is 0, for exactly the reason that at any zoom level, eventually I can't tell this function apart from the x-axis, right? This green line may as well be the x-axis for as far out as I'm zoomed. I can go in a bit more, and here I can actually tell it apart. The green line is definitely not the x-axis because I can see that little bit of daylight showing between the curve and the x-axis. Let me go ahead and turn off the minor grid lines to make that a little bit more clear. Let's get rid of the grid as well. But the thing about limits is the farther I go out, eventually I get back to this point where, oh, I can't tell the green line apart from the black line anymore. I can't tell the graph of my function separate from the x-axis itself. And I could zoom in a little bit more until I see some daylight between those two curves. But, as I go farther and farther out, well, that green curve is getting closer and closer. And eventually, I won't be able to tell them apart at this level of zoom either. Now that idea also holds for these discrete points along the curve here. Now I've been saying this word discrete a couple times. This is a math term. It's spelled D-I-S-C-R-E-T-E, and it just means separated, right? These blue dots are distinct from one another in my graph, and even though their y values are all eventually getting close to 0, they're always 1 unit apart to the right from each other. So they are going to be separated out. But the point of this demonstration is to show that we can understand the limit of a sequence by taking its formula out, if it has a formula, and treating that as a function, just the same as we would have done limits of functions in Calculus 1, and just the same as we do limits of functions for calculating improper integers.